I'm going to share with you a very simple regression. And that's in the grades. If you click this link to the grades data set to go to this grades regression, let's get a very simple contrived example of us doing a linear regression. So I'd like to invite you now to click in this grades regression. So here we have a data set of grades. I guess we have 23 rows. This data set is kind of like a contrived data set, and it's very simple. So here we have column of the student name, one for study hours and one for the grade. We're going to use one of these columns to predict the other. It might be obvious, but I just want to engage you. Are we going to probably use study hours to predict the grade, or grade to predict the study hours? Which is our X and what's our Y? What are we trying to predict here? Most likely. Grade, I think, is like our Y. That's what we're trying to predict. And maybe our X is number of hours studied. Is there a relationship between number of hours and your grade? That's what we could try to find out by doing a regression. Now, let's look at here I'm exemplifying the tail of this data set. What do we see going on in there that might be weird? Thoughts? No values. Let's look at the student called Bill. We know this student studied 8 hours, but we don't know their grade. So we don't have a label there. So we can't include that in our training data. There's no grade. There's no corresponding target to hit. So we'll probably drop that row. Later, maybe we can use it when we make a prediction. This will actually be a perfect example. Bill, the student Bill, is an example of a student who we know how many hours they study, but not their grade. So after we train our regression model, maybe we can then give our model, hey, make a prediction for Bill. If you study 8 hours, what do you predict their grade is going to be? So maybe we'll come back to Bill later and this 8 hours, and maybe we'll try to incorporate that in our predictions. All right, good to know, but we can't include Bill in the model training. What about Ted? I guess I didn't create this data set, but Ted doesn't have study hours. So how could we even try to predict the grade for Ted if we don't know the study hours? Maybe there's just some null values in the data. We're definitely going to drop these null values. It's simplest to drop them. However, sometimes what you may see is an approach called imputation or imputing. We might just use the mean of that feature for everyone else and impute and fill in a missing value, but we'll drop nulls here. So here you see us dropping nulls, df drop na in place. Now we have 21 examples. We have the target and the features for all of these records. So before we go like training a model, what we'll want to do is explore any relationships between our features. And here what we can do is preempt our prediction with a simple trend line. So, hey, here's a plotly scatter plot, and here we're plotting on the x-axis study hours and the y-axis the grade. So if we know that Bill studied 8 hours, what are we probably going to predict the grade was based on this linear trend line from our chart? Thoughts? I'd love a volunteer. 8 hours, what would be predicting the grade? 4.62. Yeah, like something under 50 here. So wherever this red line crosses the 8. So we might predict something around 40. Okay, good to know. But that's just using our trend line. Let's do this more formally. When we have many features, we can't create a single trend line like this because there's more than one X variable. So we might have to create one of these plots for each X that we have. But like, well, which one is the most important one? we can answer this with a formal regression. Whenever we do a regression, we specify which columns to use as our X and which column to use as our Y. And generally we'll go grab this from the data set. So here, just like we said, we're going to use grade as our Y and study hours as our X. Now, generally, we have many features, so that's why I'm using study hours inside a list here. It's like one of potentially many features. When we use this kind of list-based approach to choosing columns, it gives us a data frame back, and that's what we want with our features. Our Y column can just be a series, and that's fine, but here we just need to use an approach like this to keep our data frame, our X in data frame format. When we have many features, we don't have to worry about this. We'll just say, use this feature and that one and this one, and they're all our features. Okay. After we have split X and Y, we know what features we have and what our target is. Now we are in auto mode. Now we're in boilerplate code mode. Now the rest of the code that we're going to use is applicable for every regression model that we're going to use. First, we start with a test train split. What is going on here? I'm just going to do this a little different. Like, here's our training data, and then here's our test data. Let's look at X train and Y train, and then X test and Y test. Here, I need to run all these cells. So here we're importing the train test split function from sklearn, and we'll do this every time we every time we have a supervised task. And we just have to remember how to do this. Let's take a look at the documentation for the train test split function. Did I give you a link to this in the agenda? At the bottom? Yeah, train test split. Take a look at this link that I shared at the bottom of today's agenda. Let's go look at the documentation for this function. So it's coming from the model selection sublibrary of sklearn. Okay. The function's called train test split. We can use it in a few ways, but generally we'll pass it X and Y. But there's other parameters as well, like what is the test size or train size? Here we can give a number of rows or a percentage of rows. I think it'll handle either, but we'll generally give percentage. We'll generally just say test size equals 0.2, although that's its default. So we can omit the test size parameter. Here, when we look at the default, I think the default is 2.25, 25%, which is fine. So if you omit the test size parameter, it's still going to give you a reasonably split in terms of size. Random state. Has anyone heard of this parameter before? It's very common. Anyone? What's random state about?
It ensures that you can replicate your the train test with like your before already. You can set a seed for it.
Exactly.
Setting variables so that you can replicate your
Exactly. Let's always use random state parameter in our train test split. What it does is it makes sure that when we split this data is being split kind of randomly. It gets shuffled up randomly and then split. So when we split the data this time, we want the results to be kind of the same as when we split the data, when we run it again. Like when we run our split the first time in our first run of our model training, we want to get the same rows that we get every time to make our results reproducible. Otherwise, if the data that we're using to train the model changes every time, then our results are going to differ from run to run, and we can't even compare. Like, hey, we try this strategy out, what's our square score? Okay, now we try this other strategy, what's our square score? If along the process, the data that is being used to train the model is different, then how could we compare our results from run to run? So the random state parameter, when we split the data, it also gets shuffled like randomly. And so we'll set the random state. And we heard that sometimes this might be called like a seed. You might set a seed for the randomness. The random state parameter ensures that the random rows that we get are just going to be the same kind of random every time. So it's reproducible. So we'll always specify random state. And you could choose your own integer. I choose 99, but you might see 42. You could choose your own integer and make it your own as the random state. Shuffle parameter, the default value is true. So we can omit it and the data is going to be randomized. And we'll always shuffle. Shuffling the data helps mitigate against a sequential bias. So if in our data set, for example, in our grades data set, if we had all the best scoring students at the top, if these were sorted, then maybe when we split, if we don't shuffle, now our training set is just going to be trained on the best scoring students. But in our test set, we have low scoring students. We want examples of each in the test and the training set. So shuffling helps us remove any sequential bias based on what order the rows come in our data set. So shuffling the data during our split helps eliminate or mitigate against sequential bias. So we're definitely going to split the data. We're definitely going to shuffle. It happens by default. And that's what's going on with this train test split function. We're going to use it every time. And it makes our life really easy. It's going to return 4 values. So we'll use it like this. It's always going to return these variables in this order: X train, X test, Y train, Y test. So that's when we invoke this function, it's going to give us 4 arrays or 4 subsets of the data. And that kind of matches with what we see here. Yeah, we're going to split into a train and test for sure, but also there's the X versus Y component of this. Okay, thoughts or questions about splitting the data? All right, let's keep it moving. So generally what I like to do is look at the size or the shape of each one of these and verify that it got split properly and that you put them in the right order. So when we look at our training set, how many rows are now in our training set here after we split? In this example, 16. So here with our X train, we have 16 rows in 1 column. But if we had more features, we would have like 4 columns or something. Whereas with our Y values, it is just a single series of 16 rows. Now our test set has 6 rows. Not dealing with big data here. But all right, our X and Y test both have the same number of rows. Our X and Y train both have the same number of rows. So now we're ready to keep moving. But we're already in our boilerplate code section. So this code in this block you'll use every time. You copy and paste into your project after you figure out all the data pre-processing. Now that we have split our data into train and test, X versus Y, there's a particular way that we go about training our models. So let's take a look at this code block here. Here we're importing the linear regression model from sklearn's linear model sublibrary. Let's go take a look at the docs for this, which I've shared in our agenda. The nice thing about the sklearn docs in particular is that in addition to helping you implement this code, like what parameters does this function take, stuff like that, it's also going to maybe give you a background about each one of these types of models and how it does its job. So here in the docs, we see something related to like ordinary least squares. We see some kind of description. In other models, this could be even more helpful. So maybe even like reading through the sklearn documentation, in addition to helping you learn how to code this stuff, it could give you some background concepts as well. So it's very helpful. And there's a lot of tutorials here in the sklearn docs as well. But anyway, here, we said that when we're doing a regression, there are a few that we can do, but we're just going to focus on the linear regression. And here it is, capital L, capital R, linear regression class from sklearn. What parameters does this take? I think nothing important. Some of the models will take different parameters. And when we do classification, especially when we deal with like decision trees or random forests, there's certain parameters that will be important. But this linear regression doesn't really have any parameters, so we can just initialize it. So here we initialize a new instance of this linear regression model. Here we're in the boilerplate part of our codes. Again, like anytime we want to train a regression, we'll just do this. We already got the X train and the Y train, and those are the values that we pass to the model's fit function. So in sklearn, they implement, I think they call it like the estimator API or something like that. So every sklearn model is going to operate using a similar interface or API. All right, we have our linear regression model. We initialize it. Now our model exists in this variable. I called it model. Great. The model's dumb. It can't make predictions unless we train it on the examples. Remember, this is example based. So we're going to use the model's fit method and pass it two parameters always, X train and Y train. So what it's going to do is use the X train as its examples and the Y train as the answers or the labels. And that's how it's going to learn how to pick up patterns in the X data. After the model is trained, we can use it to make predictions. It will learn what it needs to learn. It learns the weights or the coefficients for each feature. And it uses the weights and the intercept as well to make predictions. What does the model learn? It learns the weights, and that's the important thing. It learns the coefficients. It learns the slopes, if you will, for each variable. Here we just have one. So let's take a look. This model variable, only after the training has been complete, do we now have access to two properties actually. And any property in sklearn that has like a trailing underscore, like this coef underscore or intercept underscore, that means that underscore, it's generally a signal that says, hey, we only have access to this property after training has happened. So we can only look at the model's coefficients and intercept after it's been trained. But once it has been trained, here we see the coefficient here is 6.3 and the y-intercept is -17. So what that means is we now know our line of best fit. We now know our trend line, and that can kind of be used to make predictions. So here, the line that we end up with is like each study hour will get you 6 new points, 6 greater points essentially. That's the slope of this line of best fit. For each new study hour, it's going to contribute 6 points to your score. And I guess the intercept, if you don't study at all, you'll get a negative grade, which is not possible. If you don't study at all, your grade will probably be 0. But it just so happens that with this data set, like the line of best fit just has like a negative intercept. It's all good. And this is like a dummy data set anyway. So that's one thing that we should pay attention to is after the training, it learns the weights and the intercept. And so the weights will also tell us if we have many features, which one is most important. So we're going to come to that when we have a data set that has many features. I would encourage you to use this code right here. This is how I like to wrap my coefficients. We take the weights, the model's coefficients, and that will be like a list of numbers, but they're in the same order as the features that we had in our X data. So in order to rejoin, to know which coefficient corresponds with which feature, I like to just create a series like this using the original features. And now that helps us label each one of these coefficients, because right now up here, when we just look at the coefficients like 6.3, sure, If we have many features, it'll just be like a list of numbers, but which number corresponds to which feature. That's why I encourage you to wrap your coefficients in a nice series, because we can always sort that later. So when we deal with many features, let's talk about these coefficients some more. But that was it. That's all we had to do to train the model. There's like 5 lines of code. First, get your X and Y, which is the hard part. Then we're in autopilot. We do a train test split. We have our X train, X test, Y train, Y test. Now we train the model using the X train and Y train. We could look into the results of training, and that's all great. But how well did we do? Now the final part is evaluation. That's when we go use our metrics. In order to evaluate the model, we first need to use the model's predict method. And we pass it the X test. Basically what we're saying is, hey, you know, in that unseen data, here, we're going to give you all of these study hours. Why don't you now try to predict the corresponding grade? So the X test is the unseen study hours. We use the trained model to make a prediction for those hours, like what's the corresponding predicted grade. Generally, we'll call this like Y pred, which is a predicted version of the Y test. The Y test has our labels. That's the real ground truth. The predicted Y, the Y pred, is what the model thinks. So now what we can do is compare what the model thinks, the model's predictions, the Y pred, against the ground truth, the Y test, that's coming from our labeled data set. So all we need to do is model predict to get the Y pred. Here, I think I'm just like looking into, oh yeah, here we can start to like mesh together the grades and the predicted grades, see if they're accurate, I guess. But importantly here, in this code cell is where we're going to go use some metrics from sklearn. Remember, when we do a regression, there's a certain set of metrics that we'll use. When we do classification, we use totally different metrics. For regression, we have the R square scored, which we talked about already. We have the mean squared error and the mean absolute error, and those are both like based on, I think, the residuals. Mean squared error is what we might focus on commonly. And so here we see R squared 0.67. How good is that? Okay, not bad, not the best. And now these mean squared error and mean absolute error are kind of like a function of the scale of our Y values. If we take the square root of the mean square error, I think that's the root mean squared error. So like if we say MSE upper 0.5, this is the RMSE, root mean squared error. So when we take the mean squared error, we're squaring the residuals, because some could be positive if they're above the line or below the line. Some could be positive, some could be negative. So by squaring them, we make sure that our mean squared error term is always positive. But it's been squared, so now if we take the square root, now we're expressing the error in terms of our original Y data set. So I guess here, the error, or the average error for each prediction, is 8 points on the scale of 1 to 100. I think that's how we can interpret this. All right. So is that good? We can predict a student's grade within 8 points. It's not bad. Like we know whether they're going to be in B range or A range or something like that. Okay, cool. So right now we have trained the model and we have evaluated it. So we're kind of done. Now, hey, remember we had those like students from before. We might be able to say like, hey, model, predict if our values were like 8 hours. I might need to do another version of this inference. So yeah, we could use the model to make predictions. So if you don't study at all, your grade's going to be negative. Doesn't really make sense, but that's what the model's saying. If you study 4 hours, you're going to get a 7. If you study 8 hours, you're going to get a 32. Remember when we looked at the line of best fit, we saw 8 hours corresponds to something around 40-ish. So that's now the model is specifically guessing 32. And I guess if you study 20 hours, that's gonna get you 100 or something like that. So that's how we can interpret the model's predictions. So this predicting unseen values would sometimes you might hear that called inference, like at inference time with new data. So how is this model that we train gonna do in the real world? We can just use that trained model to make predictions. Now, what you see also happening at the bottom of this notebook is how you could save a model to disk and then load it later. Sometimes when you're training complex models, it might take hours. So like next time you want to make predictions, you want to retrain that model for hours? Or could we maybe use a saved version of the model? In this model management section of the notebook, you could see how easy it is to use this module called joblib. We take our trained model, give it some kind of file path, maybe a pickle file, which is one way of saving this model. And joblib.dump, that means like save this model to this path. So now we have our pickle file. This is actually a file that contains your model, your trained model. And you can upload this trained model to a server and have your users interface with it or making predictions using live data. So once you have saved the model to the file, it's as easy as joblib.load from that file path. Now that gives us the same instance of our model that we had originally. We can use it in the same way, like making more predictions on that unseen data. So I'm just including this model management code for you so that you might be able to use it when you're training models that take like hours or like a day to train. We wouldn't want to train every time we want to make new predictions, so we could just save the results of our trained model. Okay, this was an example of a very simple regression.